Welcome to Chapter 1.2. Today, we are examining the strict ethical requirements of software engineering. It is common to assume that a software engineer's only real job is writing clean, efficient code and patching technical flaws. But that view ignores the reality of what modern software actually does. Take a look at this model. When an application is hit by an SQL injection, where an attacker forces malicious code into a database query, the damage isn't contained to a single server. It compromises the data those servers hold, affecting the people who rely on them. Software controls the logistics chains feeding these cities and the financial systems keeping them solvent. The urban grid functions through a digital nervous system. Here we see cranes assembling a high-rise. We expect civil engineers to adhere to strict safety regulations because human lives are at stake. Software engineers are building the digital equivalent of these load-bearing structures. This creates what we call the socio-technical framework. Code exists as one part of a network that includes human lives, legal boundaries, and physical infrastructure. Operating within this framework makes ethical integrity a mandatory professional requirement. You can write brilliant, perfectly optimized algorithms, but if you deploy them without understanding the societal framework they control, that flawless code becomes a liability. Professional responsibility addresses behavioral standards that remain invisible to the legal system. There are 4 primary areas where these professional standards apply. We can map them out on this matrix. First is confidentiality. You will frequently handle sensitive data, and keeping client and employer information secure is an absolute requirement. Even without a formal non-disclosure agreement, a software engineer is ethically bound to respect the privacy of their employer's data. Next is competence. You cannot lie about your skills or knowingly accept a job that falls outside your capabilities just to secure a paycheck. The third requirement is protecting intellectual property, or IP. These are creations of the mind, like patents and copyrights, owned by clients or employers. For example, you cannot lift a proprietary sorting algorithm from a previous employer and paste it into your own startup's codebase. Finally, we have computer misuse, which covers a broad spectrum of inappropriate technical behaviors. This ranges from trivial offenses, like gaming on company hardware, to severe violations, such as deploying malware or exploiting cross-site scripting vulnerabilities on a system you don't have authorization to test. Understanding and respecting these 4 pillars separates someone who simply writes code from a trusted professional engineer. To give professionals a clear framework, 2 major global organizations, the Association for Computing Machinery and the IEEE, established a standard. Together, they created a code of ethics consisting of 8 fundamental principles that all practitioners are expected to memorize and follow. Let's look at the structure. Principle 1 is public. You must act consistently with the public interest. Never build something that knowingly harms society. This is the overriding rule. Principle 2 covers the client and employer. You act in their best interest, but only when it does not conflict with the public interest. Principle 3 focuses on the product. You have a duty to ensure your software and modifications meet the highest professional standards. Principle 4 is judgment. You must maintain independent assessment. You cannot let bribes or pressure convince you to sign off on bad code. Principle 5 addresses management. Leaders have to actively promote an ethical approach to software development within their teams. Principle 6 looks at the profession itself, demanding that you advance the integrity and reputation of the discipline. Finally, Principles 7 and 8 cover colleagues and self. You must be fair to your fellow developers, and you must participate in lifelong learning to keep your skills sharp. You can think of this list as an ethical algorithm. It's a decision tree where the public interest acts as the absolute root condition. In a classroom, that algorithm is clean. In the real world, the variables conflict and absolute answers are hard to find. Take the conflict between safety and time. Imagine an employer orders you to falsify safety validation records for a critical system because a rigid product deadline is approaching. By applying the ACM algorithm, the solution is clear. The rules governing the public and the product strictly forbid falsifying both records, regardless of what your employer demands. But consider a second dilemma, a clash between personal beliefs and employer assignments. What if you were hired as a civilian developer and later reassigned to write software for nuclear weapon systems, a direct violation of your personal moral compass? Unlike technical safety violations, the professional code lacks an absolute answer for personal ideological conflicts. It provides a hierarchy for public safety, but it cannot dictate an individual's private conscience. This forces the engineer to perform a private risk assessment. They must calculate the scale of potential damage, identify the specific parties who would be affected, and measure those results against their own moral compass. Preventing these crises depends on setting expectations early. An engineer who communicates their personal boundaries during the hiring process ensures that their career and their conscience never move toward a collision. Technical skill makes a coder. Ethical rigor is what defines an engineer. Let's consolidate this into the 3 core areas you need to memorize for the exam. First, recall the 4 areas of professional responsibility: confidentiality, competence, intellectual property, and computer misuse. Second, know the 8 principles of the ACM-IEEE code, from prioritizing the public down to self-improvement. Third, remember the ultimate rule for resolving dilemmas: the public interest is supreme. In our next lesson, we will apply these exact principles to complex case studies, analyzing real-world systems like insulin pumps and autonomous weather stations. The socio-technical systems you build will outlive you. In the end, your ethical judgment is your most enduring legacy.